let's start our journey of the first gate. It's very trivial, but it is important. We just want to mention it. Identity gate. What does it do? I equals to 1001. Basically, it does nothing, right? Because if I apply I to any vector, and I should now use the bracket notation, it's just 1001, and I'm talking about qubits, so I only have two coefficients. Remind yourself again, it means I have alpha component of 0 and beta component of 1. They can be complex number, and this gives me what? Matrix multiplication, alpha, beta, right? Because it is 1 times alpha plus 0 times beta becomes this. 0 times alpha plus 1 times beta becomes this. So that is the identity gate. Very simple. And if you understand this, what we are going to do is just do something a little bit more complicated, right? NOT gate. Now I want to tell you, I actually should have told you in the identity gates, but I can now tell you that how we define a gate in quantum computer. We define how it rotates the basis state. That is the definition when we talk about a gate. Okay, so a NOT gate is also called X gate. Sometimes, so you just pay attention to that. So this is the definition of NOT gate. X on 0 equal to 1, X on 1 equal to 0. As I promised at the first lecture, quantum computer is the same as classical one if you don't allow it to do superposition. If you only work on the basis state, they are exactly the same. Okay? So that's why you also have Toffoli gates in classical computer. Yeah. And that is the definition of X gate. You swap the bases. 0 becomes 1, 1 becomes 0. And that's it. Right? And then, of course, then you can say, I want to see something more general. Then, because quantum mechanics is linear, then you can say, for example, you have a psi equal to alpha 0 plus beta 1. Right? Again, this is a qubit. The basis state of 0 and 1 is a linear combination of the basis state. We call it superposition. And it's as simple as you have a vector in 2D, which is 1 at 5 x hat plus 6 y hat. That's it, right? So if I apply the NOT gate to psi, what will you get? Well, I can just expand it because it is linear and it is matrix. So this is just alpha x0 plus beta x1. And I need to keep reminding myself, x is a matrix. 0 and 1 a vector. Okay? I can use the definition directly. This is equal to 1 plus beta 0. Right? Now you can have another view of this, right? I also can keep in mind about the matrix form. This is just equal to alpha beta. Again, alpha means I have alpha 0. Beta means I have beta 0. So this one tell me that the results becomes beta alpha, correct? Because now I have beta parts of 0, and I need to put 0 at the top throughout my calculation. I cannot swap the basis throughout the calculation. Same when you do your vector math, right? So from here, you can deduce also the matrix form of the X gate. X gate or the NOT gate is 0, 1, 1, 0. Okay? Let's try to, you can check it, right? But I want to use just this as an example. You have 0, 1, 1, 0 times alpha beta. The input, right? Again, psi is alpha beta. Do you agree? Psi, I told you, is alpha beta. And X gate, I just told you that this is this, right? I did not prove, but you can prove yourself. You just prove that this does give the result. And what is this? Beta alpha, right? Because 0 times alpha plus 1 times beta equal to beta, 1 times alpha times 0 times beta equal to alpha. Then you do the NOT gate. And this is like completely classical. You can do it in classical computer, except that you don't have superposition, right? Nothing special. And this is the circuit symbol. Okay, so that is NOT gate, right? Let's pause for 10 seconds and think of that, what we are doing. It turns out everything is straightforward. As long as you define how this gate operates on the basis state, then we have the gate. Because the rest, any vector is just a linear superposition. So it's easy. So instead of treating it as rotating gate, you can also treat it as swapping the coefficient. Alpha beta becomes beta alpha. There's another way, right? So if you are doing matrix, this form will help you. You're doing this form, then changing basis will help you, make it easier. Any questions?
Cascade 2 or an identity gate.
Good point. So if we put two NOT gates together, will we get identity gates? Yes, right? But I asked you to try it. But it's also easy to see. Log on 0 become 1, and then log on 1 becomes 0. So it becomes itself. So it's identity gate. Exactly the same as classical logic. Right? Another simple gate is called phase shift gates. For those who went to Tuesday's seminar, remember they talked about the Clifford gate and the T gate. The last one, the T gate. T gate is a phase shift gate. Let's see what we can try to use as an example. But let's talk about the general phase shift gate first. Okay. So the symbol is this. U, we call it U because usually unitary, but we'll look at that later. This gate has a parameter, right? So those went to a seminar here talking about many quantum circuit has a parameter, but don't worry if you don't know that. The point is just unlike the classical logic gate, you actually can put a parameter into the gate so that it performs a little bit differently. And here the parameter is talking about how much phase shift you want for the gate. That is the general definition. What does this mean? The phase shift gate applied to 0 give you 0. What does it mean? It means nothing will change. Correct? No way. Huh? Zero phase shift, or it does nothing when you see the basis, right? Very good, zero phase shift. Means identity. However, if you apply this to 1, it becomes e to the power I phi 1. Okay? If you are the 1 state, I apply an extra phase shift e to the I phi to you. Okay? This one signifies something, e to the power I phi. What is the magnitude of e to the power I phi? Someone say 1, right? If you forgot e to the power I phi equal to Euler law, yeah? Plus I psi phi, right? The magnitude is cosine square plus sine square equal to 1. It needs to be this, right? Why? What did we just said earlier? Because all the vector needs to be normalized. So if I add a constant in front of it, I better keep this one normalized, right? And the only way you can keep it normalized is just put a unit length complex vector in front of it. So it's very normal that when you have e to the power I phi. Okay? Good. So that's it. I have the definition already. Of course, I can try to write down the matrix form. I can say this is also U psi phi equals to 1, 0, 0, e to the power I phi. You probably cannot see it right now, some of you, if you did not study before. Otherwise, it's straightforward. You can construct the matrix, because if this is applied to 0, I keep 1. If it's applied to 1, I keep e to the power I phi, right? Maybe let me really quickly to show you, right? U psi phi applied to 1 means 1, 0, 0, e to the I phi. Operator 1, 0, 1, right? Because this is 1. 0, 1 is 1, right? I don't have 0 component, I only have 1 component. It's just x hat is 0, y hat is 1, right? You do the matrix multiplication. Yeah. Maybe too fast, right? I can write it as this. That would be better, right? And this is equal to this, which is equal to this. Right? So I want you to be very familiar with this, although this is not the main focus of the class, matrix, or this transition between the matrix and the bracket notation. Okay? So in general, of course, if I have a psi, right, I apply this psi phi to alpha beta, I will then get alpha, maybe I just keep the column form first, alpha beta e to the power I phi, which is equal to alpha 0 plus beta e to the power I phi 1. Yeah. So what I'm doing is just reasonable, right? Does that matter? In terms of measurement probability, it doesn't matter, right? What's the probability I can get 1 here? It's still beta squared, because in reality, the probability of getting 1, if I really calculate, is equals to beta star e to I phi negative, because you have star. You do the star, you put a negative to I, times E times beta, times e to the power I phi. So the e to the power I phi, e to the power negative I phi got cancelled. So this is still beta squared. You don't change the physics when you change the phase. But however, if you have more than 1 qubit, you can start playing with constructive destructive interference using this one. Okay? So that is why it's important. Originally, I don't want to talk about that, but now since some of you went to that seminar, right, we can then summarize some useful gates. When the phi equals to pi, then e to the power I phi equals to -1, right? Because when it is pi, cosine pi is -1, sine pi is 0. So this becomes a C gate, Pauli gate, which was very important. Okay, instead of e to the power I phi, because now e to the power I pi is -1. Okay, we also have another gate called S gate, which is the square root of Z gate. It is 1, 0, I forgot the exact number, but it's e to the power I pi over 2. So means this is what? 1, 0, 0, I. And then finally, we have a T gate, which is it's the square root of S. That is 1, 0, 0, e to the power I pi over 4. Okay? You see this square root because square root of e to the power something is just e to the power something divided by 2, right? That is the T gate. Of course, this is 1 over square root plus I 1 over square root 2, right? 1 over square root 2 plus I over 1 over square root 2. Do you see what I mean? This one, plug in pi divided by 4. Is 1 over square root 2 plus I times 1 over square root 2, right? Or 1 over square root times 1 plus I, right? This is the T gate that they mentioned in the seminar. If you went there, if you did not, doesn't matter. Is the whole family of C. You don't need to memorize them. There are few gates we care about, like the Z gate or swap gates. We'll talk later because we are going to implement those gates in the physical hardware. And we only implement a few of them because any gates can be break down into all those fundamental gates with finite precision. Okay? It's just like universal set. Yeah? But that's what I want to say. Any questions? Okay. Now, if not, right, so we're done with this gate, then we should learn something you don't find in the classical computer. And this is the Hadamard gate. Okay? So what is the definition of a Hadamard gate? H gate. We already see that. When you apply to 0, it becomes 1 square root 0 plus 1. The main point is it creates superposition. But that's why Hadamard gate is so important. Because we said that quantum computing rely on superposition and entanglement, right? So you need Hadamard gate, which is plus by definition. We call it the plus state. And when you apply it to one state, although I go fast, right? But the concept is the same. You do need to go back to review if you're not familiar. What do you get? Minus. It's also a superposition. But there is a phase difference, right? This phase is what? Pi. E to the power I pi. Like we'll just discuss. So, yeah, you just play with the matrix. You find that it means the Hadamard gate is 1 over square root 2, 1, 1, 1, negative 1. Memorize it. 1, 1, 1, negative 1. Okay? It's not difficult to memorize. And this is the symbol. Again, nothing special. And yeah, I think now the insight is this, right? You don't want to make yourself like a computer. If I ask you what is alpha times 0 plus beta 1, of course, you can just plug in this. But because you're inside, you understand what it does is convert 0 to plus 1 to minus. When you're playing with quantum computing algorithm, you know immediately this is U alpha plus beta minus. Correct? Because convert 0 to plus, convert 1 to 1. If I try to write it in matrix form, you need to be careful, right? To be super careful. This is alpha beta. You're right. This is alpha beta. But this is alpha of 0, alpha of 1. This is also alpha beta after applying the gate. But this is alpha of what? Plus, alpha of minus. Yeah? So be careful of this, right? The last thing I want to tell you is, maybe I will just save the time, is what is Hadamard gate times Hadamard gate? Just go through the math. And it's not difficult. It's identity gate. So it means Hadamard gate is the inverse of itself. Okay? The inverse of Hadamard gate is itself. This is very useful later for some calculation, right? Memorize. So Hadamard gate is something very important. Okay?
You can say like H of 0, if we pass it through Z gate, it will give H of 1.
Can you say again? H of 0?
H of 0.
Pass
it through
Z
gate.
The Z gate. This gate.
Yeah. Then it will be giving H of 1.
Yeah. You're right. So we pass H applied to 0, you get plus, and then the plus, you apply the Z gate, then you will get minus, correct? Now, so we're done with the single qubits, right? Are you okay? It's a matter of practicing, play with the matrix, and understand the definition. That is very important. I feel this is very important. What is the meaning of a gate? It tells you how it transforms the basis state. Always step back to that question. Once you understand how it transforms, the rest is just a linear combination, distribution law, right? But now we can create superposition, right? But one qubit is not useful. And also we need entanglement to have good quantum computing. So we definitely need to have